Welcome everybody to Weekly Quantum World Detangled, Season 1, Episode 10. It's our birthday today. We are going down under to Macquarie University with our special guest Gavin Brennen. Denise will share her business tip on some fundraising news once again. The industry is hot. Tommaso will talk about quantum computing with neutral atoms and why they do not come out of Switzerland. And we will discuss topological quantum computing and quantum sensing with Gavin on. Today, as usual, I'm joined by my friends Denise.
Hi everyone, Denise Ruffner, Cambridge Quantum Computing. Happy to be here. It's a nice sunny day in Southern California. And Tommaso.
Hi everyone, good morning. Tommaso from Entropica, calling you from Singapore. Also a beautiful day today, 9 a.m. And also very happy that Professor Gavin Brennen from Macquarie is joining us. So Gavin.
Yeah, great to be here. Good to see you again, Tommaso. Maybe I'll just do a brief introduction. I grew up in Alaska, did PhD studies in New Mexico, which actually has a really strong quantum computing and quantum information effort for quite a long time now. And then did postdocs at NIST in Gaithersburg, Maryland, and the Institute for Quantum Optics and Quantum Information in Innsbruck, Austria. And then I've been at Macquarie University for the past, it's been 12 years now. And life is really nice and easy here. The news is much less insane than it is in the US. It's actually a pretty pleasant place to be right now, relatively inside this COVID-afflicted year of 2020.
And it's a little bit the opposite of Alaska, I'd imagine. Did you live in the outback or the big city? How does that compare to your native?
Yeah, so I was one of those city folk of Alaska that lived in a size city of 40,000, Fairbanks, which is the second largest city. You could say life is quite tame here in Sydney compared to Alaska. Although we have different creatures of different deadly capacity here, like spiders and snakes and jellyfish. But yeah, it's
as we do in Miami. I saw my first crocodile recently, and I didn't mention that I live in Miami on our last episode, and our viewers did not appreciate that. So I'm still calling from Miami. Denise, you're originally from Austria, right? Gavin. How was Innsbruck and how much time did you spend there?
Yeah, I was there for 2 years. It's great. It's a mountain town. You're surrounded by fantastic ski slopes. You're so close to Italy where the really good food is, but there's also like there's some pretty interesting people that come through Innsbruck. It's a fun place.
Yeah, Gavin and I were talking about Austrian food prior to the podcast. We haven't eaten dinner yet, so I'm hungry. It sounded good.
Oh yeah.
Mozartkugeln, my favorite dessert, a little chocolate ball. Marzipan. Love it. Give it a try. Let's look at the news.
Great. Well, everyone, exciting news out of Singapore this week. Horizon Quantum Computing received a seed round of funding for about $3.2 million US. I think it's a great endorsement of a very strong startup and a very strong team. Really exciting news. And I wanted to point out a discussion that I had with André prior to this call that really the quantum tech investment space is hot right now. In fact, this year we've seen 33 total deals by investors with an average deal value of about $13 million. So about $387 million raised to date in quantum computing, which is pretty amazing. And I think André has more details on this as usual, our data guy.
Of course, we will give you a preview of the data. It's not finished yet. It's in draft version, so forgive the poor formatting. But as Denise pointed out, this has been a record-breaking year so far, and actually second quarter with a total of 386 million that we were able to track and verify. What's interesting here, you see funding by week here, and I took PsiQuantum out of this graph on the left versus the right one, so a different scale, just to unskew the data a little bit. But much of this funding has occurred really over the last few weeks, and the year started out kind of slow. So this talk about quantum winter certainly accelerated funding in quantum technology, and is hopefully turning it into a quantum summer. What is also interesting to see is when we look by investment targets, so the companies that are being invested in. Obviously, Canada, the US, still going very strong, but we're seeing more and more activity in Europe. Our good friends at IQM, and they are always happy to take more money. Give me a call. In the UK and all across Europe, France, we will be talking about a French company soon here, are really seeing some traction, and the sources of capital are diversifying as well. As you can see, we have India on the map now with some investments, and this is all private capital, as you see in this pie chart, really professional investment capital. And Europe is getting into the game in a big way in terms of funding it. Also very, very interesting, quantum computing hardware and full stack companies make up a total of 88% of that money. So the Tommaso raised some money, and he's in software and Horizon, but the bulk is really going into hardware, which is good to see. And we have a breakdown of rounds as well. Obviously, later rounds are bigger, but we're starting to see that these rounds are spreading out from still very strong seed and bridge rounds into A, B, and D rounds. So a healthy and growing ecosystem, which is good to see.
Thanks for that analysis. It's newsworthy. I think a lot of people are still talking about quantum winter, and I think this will be very encouraging news.
Yeah, indeed. Interesting. Very interesting. Thanks,
so,
André.
Tommaso, let's hear about the paper of the week.
Yeah, let's do that. So I'm going to present. Just give me 1 second. This is maybe not a scientific paper in the strict sense. It's actually a white paper released by the team at Pascal. So Pascal is a French company. They work together with Quantonation, here represented by Christophe. And just a few days ago, they released this manuscript called Quantum Computing with Neutral Atoms. So it's very interesting. I think this is a very fascinating technology. They are not the only company pursuing it, which is fine. I just like it because, as we will see in a second, they are looking at a maybe different way, or at least a way which is a little different compared to what people are most used to process quantum information. I also very much like the fact that they give evidence of how they can scale the technology up to, let's say, 1,000 qubits range, as highlighted here in green. But if you allow me, I'll scroll down a little bit. By the way, the paper is quite easy to read. It is broken down into the technology and applications of what they call the Pascal QPU, the quantum processing unit. What I find very interesting is that, just give me 1 second, when it comes to the stack, as they describe it, if you look at the middleware, if you like, which is what they call the quantum software, there are actually 2 boxes that show up. One is a digital control box, and the other one is the analog control. What does that mean? People who are familiar with quantum computing, they will know that usually a quantum computation is understood or is performed as a sequence of gates. So you have a quantum circuit, you break down your computation or the evolution of your quantum system as a sequence of discrete gates. What the Pascal team is working to implement is something called analog control, which is slightly different. So what you can do, and there is another better picture down here. Here. So instead of doing digital processing, so instead of having only gates, they can also support something known as analog processing, where they perform the whole Hamiltonian evolution directly. This is very intriguing because for certain applications, it might, it might help, and the conditional is always, of course, important, it might help to overcome some of the issues in terms of noise that are associated with digital processing. So this section 2.2 for interested readers. Overall, very good results, very excited about the technology. Another good point to make is that it can potentially support multi-qubit gates, so not only 2-qubit gates, but you might be able to entangle all of the atoms on the array. Maybe the last point is that, like for ion traps, here you're using natural atoms, so you don't need to artificially build qubits like you would do on a superconducting chip. And you can also support 2D and even 3D geometries in theory, which is again different from the way ion traps are being constructed today. Yeah, it's great work. Very happy that they released a white paper.
And I hate to say, I didn't influence the choice of this paper, but CQC will be issuing a press release with Pascal in the next week. So we're very excited about Pascal as well and their technology.
Good to hear. Good to hear.
Yeah.
That's great. Okay, so since Gavin is here with us today, I think it will be really great to pick his brains on some interesting concepts in quantum computing. First of all, thanks again for joining us. It's always great to see you again and to talk with you.
Absolutely.
Thanks. I think a great way to start would be to go back to some of the research that you've been doing. And I know you're very much interested in topological quantum information. And if I'm not mistaken, there was a great paper, a good result last week on the subject. And maybe I just would love to hear what you think about the technology that Microsoft is pursuing quite aggressively, and what you think about the latest results and where we are at.
Sure. So I happened to be in an audience where Alexei Kitaev, this was in like 1999, he gave a talk on how one could use anyons to perform robust quantum computation. And in the audience, people were like, anyons, really? Maybe. But non-abelian anyons? No way. And like and these are like some big theorists in there saying there's not a chance. I mean, it's beautiful theory, but no way. And it's been a long time. So just for the listeners who may not be so familiar, the idea behind topological quantum computing is that we can try to build in a lot of the error correction and tolerance to noise into the hardware. So you sort of imagine you do your computation on a 2D surface where you make particles, and all the gates are done by just winding one particle around another. And it's thought to be robust because there's an energy gap to create excitations, which would screw up that computation. And also, you don't have to be extremely precise with your gates. All you need to do is just make sure that one anyon goes completely around another one. So it's got robustness in terms of processing and against noise. But it's, we don't find nature doesn't just give us anyons. You have to manufacture them. And it's been, 23 years since Kitaev originally proposed this idea. And we still don't actually have an anyonic gate. But there was this really exciting news that you introduced with that there was results from some groups in France, which showed the existence of abelian anyons in a fractional quantum Hall system. So this is what's called a 1/3 filled fractional quantum Hall system. And they actually showed that if you, using what's called a double point contact interferometer, which you basically take the interference between a particle either going around another one or not, and that has a relative phase. And that phase is predicted to have an angle that's given by 1/3 times 2 pi. And that's exactly what they found in the experiment. So it's a really exciting result. And it's a vindication of theory that goes back, back to the days of Wilczek, who was looking at these things in the 80s. So now abelian anyons aren't actually universal for quantum computation. You can't do a set of gates on a degenerate Hilbert space, but non-abelian anyons can do that. And there's a big effort at Microsoft to produce and braid non-abelian anyons. And their major effort is using what are called nanowires, where they get anyons in the ends of wires, also due to a proposal by Kitaev. My personal opinion is if they show convincing evidence of non-abelian anyons, this will be a Nobel Prize. And then the effort will really be on to showing whether braiding is robust enough to make it a competitive platform for quantum computing.
So what does that mean in terms of actual machines and them being available? A lot of progress has been made recently, right? New superconducting champions coming out every other week, ion traps making a lot of progress, photonics, at least, psi quantum, a lot of news and amazing funding. Where are we at? What's kind of the timeline, and what should we expect?
So I think there's no doubt, I think most people in the community would agree with this, that the topological approach is well behind those other approaches. Ions have, very high quality measurements. The 2-qubit gates are extremely good, down to the 99.95 to 97 level. Superconducting circuits are also very good. The scalability of the photonic systems is excellent. So topological has a long way to go. It's definitely behind. And even if they do get it working, it's more than likely that what you'll need to do is combine topological qubits inside of a software-based quantum error correction code. So you might say, okay, I'll take a qubit formed from anyons, which you can do from 4 anyons, and then use that qubit as a physical qubit in maybe a toric code, which involves, a lattice of these things. So then it's going to be a question of balancing of resources. And we're getting to the point now where people are paying a lot of attention, including investors, on really what are the resource requirements to make gates fault tolerant for scalable quantum computing, at least for problems of interest to industry. And then the hard work has to come out, looking at, can we actually reduce the amount of resources enough with a topological approach to make it the right investment? And clearly Microsoft has taken that opinion that yes, it is worth that investment. I personally, it's quite an elegant solution, I think, to make nature do a lot of the work for you. But until we see concrete results of existence and braiding of these anyons, we have to consider it, in my opinion, a technology that's behind the others.
That's fair, and thank you for the answers. It's very fascinating, and the reality is I would love to talk about this more, but I also want to be considerate of everyone's time. So I might move the focus slightly away from topological quantum computation and start looking at another topic of interest of yours, which is quantum sensing. And I quite like this conversation where we are talking about concepts that are maybe not so mainstream today in quantum technologies, at least. And the reason why I'm bringing up quantum sensing is because we all love to talk about quantum computing. I think quantum computing is a bit more intuitive when it comes to why it's useful, but quantum technologies is more than just computing, and sensing is another big area that people are starting to discover and appreciate. I know you've been doing some work on that. What are your thoughts on how quantum technologies could help with sensing, and why should people, investors, and industries be excited about that?
Yeah, right. So there's a lot of different areas where sensors can play a role, and the nice thing is you don't have to get to some dreamland of making fault tolerant thresholds. Like even sometimes factors of 10, even factors of 5 can make a big difference for industry. So for example, in mining, Companies like BHP Billiton, they look for diamond mines, and basically they use gravimeters to do this. You look at, you can stick a gravimeter on a small plane, and then just fly the plane over a region of Earth, and you look for density fluctuations based upon variations of the gravitational field. And from that, you can say, okay, this is a good spot to mine. And it saves a lot of time. It also is much better for the environment. You can do other things like look for aquifers, or look for cavities, which could be used for carbon sequestration. So there's a lot of things where just having a small but important factor improvement in the precision makes a big difference. So some big areas where this is true are gravimetry, measuring the gravitational field, inertial sensing for navigation. This is for aircraft or for submarines, and frequency standards for clocks. We're in cases where you might have GPS denied environments and you want to know where you are. You need to have very good clocks. It goes back to the old problem of wanting to know what longitude you're at, and being able to sensitively measure electromagnetic fields for like high precision advanced material technologies. You really want to know whether your device is going to work, so you need to know whether electric fields are going to be beyond some threshold. And in medicine, there's being able to have in situ measurements of reactions happening in cells. So all these things can benefit from small but significantly enough improvements in precision. And quantum materials can provide that essentially using entanglement, which is not at all possible with classical systems, as we know. So yeah, I think there's a lot of opportunity in industry to absorb these quantum technologies fairly early on, or at least in the midterm. Two areas I've been looking at are using what is called magnetomechanics to improve gravimetry. So that's where you would have a levitated superconductor, which could be put into a Schrödinger cat state. So like be split in space. The plus state would be up, the down state would be down, and there would be a relative difference in the gravitational field seen by those two components. And you could then infer that by measurements and have a very sensitive measurement of gravitational fields. And another thing I've been looking at is measuring electromagnetic fields using ensembles of spins, which you might get from using nitrogen vacancy centers in diamond, or using Rydberg states of atoms. So yeah, I think there's a lot of potential here, and certainly it's something that's uniquely quantum. That for these kinds of improvements, you're looking at an improvement from a precision that scales like 1 over the square root of the number of spins you have to 1 over the number of spins. That's the essential argument. Yeah. So yeah.
Yeah, this is really excellent, and actually, that really brings me to a follow-up question, if you like, which is, so we've spoken about topological quantum information processing, about different applications of quantum sensing. So I'll make a bit of a blanket statement, which is the following. Do you think for these technologies, the problems ahead are more of an engineering nature, or do you think there is still fundamental physics that needs to be developed before they can become industrially useful technologies?
Yeah, that's a great question. Actually, maybe I'm a little biased because I'm a physicist, but I actually do believe there are very important fundamental physics questions to be answered. And a key one is kind of an obvious one. If you have a system which is entangled and is very sensitive to some field you want to measure, it's also going to be sensitive to things you don't want to measure. So that's the sense of decoherence also increasing with entangled states. And there's this constant battle of how can you make a system that's sensitive to the field you want to see, but not be destroyed by other sources of decoherence. And, the first thing you think of, like when you take a course in quantum computing, is, all right, let's throw an error correction in there. Error correction codes work great for doing that kind of thing. So the philosophy would be, the field I want to measure is the processing I want to do on my code. And the stuff I don't want to measure are errors that I could correct. But in truth, we don't have a really elegant solution to this problem. There's some partial solutions for how you can do, you can combine quantum sensing with quantum error correction, but it tends to be very resource heavy. And it also assumes oftentimes certain structure to the noise. So what we need are creative people out there who can come up with elegant solutions which maybe could correct for the most likely kinds of errors, but still not require a huge amount of resources. So this is something I've started to look at with my student recently. And I think it's really quite open territory to find these kinds of creative solutions.
Creative people and amazing people. This was the 10th episode of Quantum Weekly World Detangled, and we've had 7 amazing guests so far that just seem to be getting more and more interesting. Thank you to my co-moderator and host, Denise, who puts a lot of hard work into this. Thank you to my friend Tommaso and Entropica Labs, that's now an official sponsor. OneQuantum.org, our startup community, is an official sponsor as well. You can find this video and every other video together with all links, papers, business tips on our website, quantumworlddetangled.com. This was season 1, episode 10 of the weekly Quantum World Detangled. You are now detangled.